Hey everybody, Lars here. Getting in front of my laptop one last time for Python for Data Science Fall 2016 because I want to just talk a little bit and show you some code that has to do with data structures. We'll talk about it in a second. Later on at the end of this video, we'll go over some announcements and we'll do some stuff as far as getting you ready because it's crunch time. We only have 2 more weeks left. Less than 2 weeks, actually. We have this weekend, the coming week, then the weekend after, then a few days. I am going to try and give you an extra couple of days with your final project. I'm going to extend this unit, but we'll get all that when we get to announcements. Basically, what we're going to do today is we're just going to go over the 4 basic data structures that I review in Unit 6, but we're going to glance over stacks and queues, then we're going to concentrate on linked lists, then we're going to glance over binary trees. I don't even think we're going to look at any code for binary trees because like I always say, I want you to be aware of this stuff and I want you to be exposed to the concepts and I want you to be exposed to the terminology, but I don't want you to spend a month working with these things because frankly, we don't have the time. I mean, you have been exposed to imperative Python, object-oriented Python. Now you're getting data structures. You've seen data science concepts along the way. It's only been, it's only 15 weeks. There's only so much we can do. So I do want you to see these data structures. And like I told you, if we were in that class, companies are interested in making sure that when people come bouncing out of an analytic master's program, business of science, they do know a little something about data structures and they do know something about linked lists. So we'll concentrate on that. All right. But first, let's look at stacks and queues. I think I have the Ludum Dare. I will tell you about that later. That's going on right now. That's actually a game jam, but we will deal with it later. I could just leave this up. Stacks and queues. A stack as a data structure stores our data just like a Pez dispenser does. Okay. What we do is when we have something we want to save, we push it to the top of the stack. So as you can see, all those items going in this drawing here, we're putting a 31 in the stack. So then when we pop the stack, the first thing out will be the 31. Okay, last in, first out, just like it says down here. So if you wanted to get that A out, you'd have to pop the B, pop the 12, pop the 3, and then you would finally be able to get access to that A. This, in a computer science context, if you think about it, is just memory. It's remembering what I did before. What did I do before that? Okay, what did I do before that? And it's kind of a way when we do tasks in computer science, it's, okay, I'm doing something. Well, let me go look if I need to do this. Oh, I do. Push this stuff to the stack, go do what I have to handle. Then when I come back, I pop the stack and my old task is right there for me to do. Stacks are like ways computer scientists in the 50s and 60s and 70s dealt with memory, with remembering what I was doing the second before I was doing it, okay? Which differs ever so slightly with the next thing we are going to look at, queues. A queue is less about memory and more about scheduling because a queue, you don't do a push and a pop with a queue, you do an insert and a delete. And when you use a queue, you use first in, first out. So it maintains the order of which things entered the system. And if you think temporally, things enter the system either before you or after you. So by using a queue, you kind of maintain order. And it's a good thing for scheduling purposes. I know what's in front of me. I know what was in back of me. And if you want to do scheduling like what we do with operating systems, if you write operating system code, you have jobs, and those jobs have to be scheduled, and they have different priorities. So what you do is you put those jobs in a queue, and if they all have the same priority, then you run them in a row. What came in first, then run that. What came in second, then run that. So a queue is a data structure that's kind of used for scheduling purposes to know what came in and what came before. I'm going to run some code, though. I think I got some code waiting for us. I do. Stacks.py is, of course, going to be up on Sakai when I'm done with this. Let's run this bad boy. All right. And let me put all this right next to each other so we can see it. So, 2 considerations when we look at data structures and we're using Python. Number 1, because of lovely Unit 5, we are now all aware of object orientation. So a lot of object-oriented techniques lend themselves to data structures, because what do you have? You have the data, the actual place where everything is, and then you have methods and ways that you can use that data. Doing a stack is a perfect example of that. We're going to use a list, because it turns out a list is a data structure, and a stack is kind of like a list. So when we want to add something to the stack, what do? We do an append. Okay? Now the second, an append is just a method. That's where I'm going with that, is that the object orientation is rather convenient. I actually have my leg out of the boot and out open in the air, and it's itching me to no end. Hopefully I won't be leaning over and scratching it too much during this video. I digress. All right. Object orientation is important when we're thinking about these things. But the second thing is that we've got Python. Python is made for computer programmers. Python is made to be readable. Python is made to be easy to use. So all of these data structures that we're going to run into, they're already written. They're already sitting there. There's a library called collections. And a lot of these data structures that we're going to talk about later, binary trees, linked lists, blah, 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 there's code for it made already. Okay? What we're going to do to use a stack, to implement a stack, is we're just going to grab a list. And for our push, we're going to use append. And for our pop, we're going to use pop. Stack has a method called pop, okay, which takes from the end of the list where the object was inserted. So it acts just like that Pez dispenser. The last thing in is going to be the first thing back out. And we see that behavior when we run it. Look, I get it. Stack 1, I'm going to grab a list. Stack 1, append test. So test is in there. Stack 2, append, I'll even draw it. Look at that. I'm even going to give you some added drawing stuff here. All right. Stack 1, append, test. So test. Ho, 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 ho. Not that good writing with the mouse. So test gets put in our list. Stack 2, append 2. What gets put on top of it? 2. Oh, that's a bad 2. Stack 1, append, test 2. What gets put on top of the stack? Test 2. All righty, Rudy. Wow, that's bad. Okay, so append, test, append 2, put it on top of it. We're dealing with a stack. Stack 2, test 2, boom. So now we print our first look at stacks up here. You see it right here. And now we pop the stack. What's on top of the stack? Okay, last thing in was the first one out. Oh, I'm scratching the leg again. That's 2. That's 2 times I'm going down for a scratch. Oh, my goodness gracious. I should get a scratcher so I can just do it from up here. What do we see? Test 2. All right. That was popped, so it's off the stack. We do it again. Stack 1, pop. What do we get? 2. Just like here. We stack it. Now, if we were to look at that stack and we don't, we would see test as the last thing there. We can do whatever we want, though. Show. Now, if we rerun it, we pop that test right out of there. So we pop the last thing right out. Okay? Whereas if we use queues, now queues are a different beastie. When I do queues in Python, I import a class called DQ, and I get a DQ object, okay? And then I use it as my queue. If you go online, I'm not going to go crazy about it, but if you go look at collections and you go look at DQ, you'll see that's what you want to use if you use a queue. So what do? I add test. That's bad. Then I add my 2. Then I add test 2. So now, because it's the method that we use with DQ, instead of a pop, I use what's called a pop left. Okay? So I'm going to go grab a data item from the other end of where I would grab it if I used a pop when I used pop left. Because this is a queue, what are we going to get when we do a pop left? We're going to get test. We're going to get the first thing we put in. And as you can see, it's what we get right here. Now we look at queues, test. Pop left again, we get the 2 because it's in the middle. We did that last pop left, we'd see test 2. Because I'm crazy like that, we're going to do it. Queued. Run that baby again. Look, test 2. So that was out there. All right. So do not save that. So that's how we're using stacks and queues. A stack is a Pez dispenser. The last thing we put in is the first thing that's coming out of that bad boy. We use it for memory and remembering. Okay? Queues for scheduling. It remembers order in a temporal sense. What came before me, what came after me. Okay? The first thing I put in test is going to be the first thing that comes out. FIFO. LIFO, FIFO. Okay? So those are the simplest data structures. There are always, like I've said before, you go to university for computer science education. First thing you're going to get is intro, some simple topics, some analysis, algorithms, sorting and searching, recursion. You'll learn your first language. It's a lot of stuff, actually. Second course is always data structures. It used to, when I was a kid, it was the weed out. If you couldn't hack data structures, then you weren't going to be a computer scientist. And that's almost always you start with stacks and queues. That's an easy way to ease people into the idea of, oh, okay, there's different ways we can organize our data. And when we organize our data in these certain ways, then there are time-tested algorithms that we use. In your slides, I'm not going to do it here, you see how I show you how you can do equations with Polish notation and use stacks to separate the operators and the operands and actually create a little calculator that does, you know, calculations for you. There's different algorithms and things like that for stacks, queues, for all of these data structures. All right. So that's pretty much the skinny on stacks and queues. I'm going to keep moving because this is going to be a long video if I don't get my rear end in gear. I am going to put stacks.py up for you in your resources. Now, I think what I want to do next is I want to go grab a drawing surface again. Let me grab red ink. And we are going to talk about the third data structure we want to talk about in this video, linked lists. This is the story. First thing we're going to do, I guess, is that a linked list introduces the concept of something called a node. And a node is where your data isn't just one single entity anymore. Your data is inside of a package that carries it. And this package comes with extra information almost and metadata. In the case of a linked list, you would have a node and it would have two sections to it, okay? You would have what's called your payload or your data in one part of the node. And then in the second part of the node, you would have something called a pointer. And the pointer, all it does is it points to the next item in your list. So this, I'm just going to do the N. I'm not going to do the whole word. This is a node, okay? So this is the story. Back in the day, you had a list. We called them arrays. And if you wanted to store your data, you would have your array. And you say, I have a 2. Okay, I'm going to put 2 in the 0 spot. And then I have a 3. Okay, I'm putting 3 in the 1 spot. Okay, I have an 8. So I'm going to take an 8. There's a badly drawn 8. And put it in the 2 spot, and everything is good. And this is the way we're going to do our memory. There's a problem with this. And I'm going to take this away. Back in the old days, memory was scarce. It was not as plentiful as it is these days. So it was difficult sometimes to get a lot of different memory spaces. And it was especially difficult if you knew you needed a lot of memory, if you needed 2,000 spaces or 3,000 spaces. Storing data the way that I just showed you is putting data in what we call contiguous memory, memory that is next to each other and right there waiting to use. Well, it turns out that there wasn't a lot of memory to use, and as computer programmers, people were looking for techniques and ways to utilize all of the memory that was out there. So one of the ways people handled memory management was with these linked lists, because linked lists don't require your data to be contiguous. Let's say I have a node here, I have a node here, okay? And it could be anywhere in memory. I'm going to do one more. I'm going to put one more right here. And these D's just mean data for payloads, okay? All right, let's say I have the top portion of my linked list right here. That's usually called a head. We're going to draw it a little better next time. And let's say it points to here. So now this is the second item in my linked list, okay? And then let's say this one points here. So that's the third item in my list. Then this one points here, okay? So now I have 4 items in a list, and they're not next to each other in physical memory, but logically they're next to each other because I had data, then I said where to go to get the next one. Data, where to go to get the next item. Data, where to go to get the next item. So if I want to add to this list, it's real easy. I can go get a memory location anywhere. Okay, it could be anywhere in memory that I get a new location, and all I do is I go to my last node in the list and I make it point to this, and now I have increased my linked list by 1. Okay? It's that simple. And because the data doesn't have to be contiguous, I don't have to tell the program beforehand how many spaces I used. So I don't have to allocate that memory. I can do it on the fly. This was called dynamic memory allocation. And by utilizing linked lists, we could do dynamic memory allocation. Oh, I ran into a spot where I need some memory. Well, now I can automatically go get it. Okay? As you can probably imagine from looking at this drawing, it's easy to delete something. If I want to say delete this item right here, what's currently the third item, all I have to do is break this link, okay, and have this item now point to this one. All right? You're never going to look at this now. That's dead out in space. Don't get me started. I'm talking about garbage collection with C++ and Java. But this guy's out in space right now. First item up here on top points to the second item. Second item right here now points to this item. So in essence, you've deleted this. Okay? Now let's say I want to insert an item. Let's say I have a new item and I want to insert it in between the first 2. Well, what I do is I break this, and I take this and I point it at this, and I take this, I point it at this. Done. So now this is no longer used. I go from the first one down to this one. Let's give it some data. Then up to this one. That's been deleted, so now I go down to this one and then down to this one. So that's the concept. Look how that looks like a child drew it. That looks like a little kid drew that drawing. So that is the basic concept of a linked list. I'm going to get rid of this. I'm going to start from scratch. Watch me work. Don't save. So from a programming standpoint, with object orientation, we want to do 2 things. We want to get 2 objects here, and I'll show you the code in a second. And it's the code you're going to work with for your homework, and you're going to see your homework's easy because I'm giving you the code. All you have to do is really augment it and add a little bit of functionality. And if you can understand what's going on here, it'll be easy to do that. All right, you got your little node, okay? But this is just a node. Let's have a data structure called a linked list. And it's going to handle 2 things. It's going to, 1, it's always going to know where the first node is, and that's called the head. So we're going to make sure it knows the location of the head. And the second thing we're going to do is we're always going to know how big we are, okay? We're always going to know the size. So when we have a data object, the head is going to point to a node. And let's say it's right here. Boom. Okay? It's going to point to that node, and then this node is going to point to another node, and then this node is going to point to another node. And every time we add a node, we click 1 to size. So we'll do a plus equals 1 to our size so we can keep track of it. And when we delete one, we would decrement from that, and boom, boom, boom. And that's basically the way we're going to handle a linked list. Enough of this drawing. Although we'll be back because I'm going to do some data structure stuff. I am going to, where's my linked list? Right here. Look at this, piece of cake. That is just a simple class for a linked list. I have 2, I was going to say where, I thought I had 2 classes here. Indeed I do. One is the node and one is the linked list. And as you can see, the node doesn't have any methods. It just sets up 2 points. It has your payload and it has your pointer, but here your pointer just points to a variable, okay? I'm not even going to get into it, but if we were using C or some other languages, you would have an actual memory location in there. But for our purposes, showing you things with Python, I'm just going to point using a variable name. But when when you use C or you use assembly, you use real memory locations, and you get down to the nitty gritty. You tell it exactly where to go while you're running your program. So the node really has all those two things we talked about, the payload and then pointing to the next item. Then in the class linked list, what do? We set up our linked list. We have our head. We have our size. And then we have a method called insert. Okay. If it's not the head, we make it the head. It's kind of like we're pushing things down the line with our linked list here. We're not attaching it to the end. We're making it the first item because you can see self.head. We're going to use the node that we accepted here. Okay. And you're going to see that when I run the code. And then I'm going to add one to size. Done. Okay. Now, else, if it is the head, we do something else, but don't worry about that for now. Get size, I just return a variable. So I'll always know how big my list is. Okay. And then I put in a real quick method to print the list. Okay. So I just make the node equal to self.head, and while my node, I just go down the line and print the next node, print the next node, print the next node. Okay. So when I run this code, nothing happens. Uh-oh, nothing happens. Why? Why? Because it's a library. I have another piece of code here called useLL here. Actually, let me put this here, this here, and this over here so we can see it all. All right. I have a thing called use linked list over here. So I grab the linked list and I import it all. And I grab one, I put it in something called my list, and then I use the insert and I start putting names in there. These are names of kids from the place where I used to teach enrichment students who were in 7th and 8th grade in New Brunswick. Good kids. You'll see I make a node of the payload Lars, and then I insert it in the list. So just like here, I'm giving it a node because that's what it wants. How does it know what a node is? Because it's right here. It's defined. Okay. I do the same here with Alex. Then I run get size. What does get size does? It just returns self.size. So now if I run this, you see 2, 3, Abby, Michael, Alex, Lars. So let's take a look at that. Well, actually, let's look at the code to look at that. What am I doing here? I'm inserting Lars. I'm inserting Alex. Then I'm doing a get size. Get size returns 2 because I've only got 2 things in there. I insert Michael. I do a get size. Now there's 3 things in there. See? Then I use my print method. Print the linked list. What do I print? Abby, Michael, Alex, Lars. You see the order in which it prints it? It looks backwards because it's taking this and it's making it the head of the list. So it's basically pushing it down, pushing it down. It's almost like sort of like a stack behavior in our linked list, which is fine. I mean, if you think about it, the stacks that we're doing are lists, but there's nothing saying that you can't implement a stack on top of a linked list. Oh boy, that's confusing. I don't want to confuse you. But there's nothing stopping us from doing that. So technically, the second thing in the linked list is Michael, because Abby's the head now. Abby's the last thing we put in. Abby's the head. Second thing is Michael. Third thing is Alex. Fourth thing is Lars. Okay, that's going to come in handy for you because I am going to give you a homework assignment where you're going to have to print. I think you're going to have to print the second thing or the third thing or something like that. I forget. But I'm not going to do your homework for you. But I mean, what if I just did this? Just to be a joker. Every time I go through, nothing happens because it is a library. What if I came here and reran it? Oh, look at that. Interesting. So now I print 1, 2, 3, 4. I print it down the line. Okay? That might come in handy. I'll even leave that there. Did I save it? Yes, it did. And I'll put linked list and use LL, which is use linked list, up in your resources for you. You're going to have this code. I'm giving you this code. So you'll have a linked list to use and play with and play with the code and to see how it works, okay? And then when you do your homework, I do believe the homework is just going to be find the second item and print the second item. And I think you might be able to do that by looking at this. Yeah? Yeah? Okay. I can't remember. I think the extra credit assignment is to use another data structure in order to print the linked list backwards. So think on that one. If you read the slides and look at this video and think about things clearly in your head, you should be able to do it in 3 minutes. All right? But it's for extra credit, and if it's breaking your brain, then don't worry about it. All right? All right, so that's linked list. I'm putting all this up on resources for you. You're going to be good to go when you have that. The last thing we're going to talk about, and I'm not even going to do any code with it, is binary trees. Now, you already are familiar with the concept of a node now, because we are experts with linked lists. But you've got to remember, that's not the only kind of node there is. There is another kind of node, the node of a binary tree. And that node has the payload in the middle. And then on the left side, you have a pointer. And on the right side, you have a pointer. And on either side of these, they're called leaves. And they point to another node. Data, boom, boom. And they point to other nodes. Okay? You see what's going on here? So classically, when we see a binary tree structure drawn, we see something like this, where each of these little dots is a node in the binary tree. All right? And sometimes we have leaves on the right, and sometimes we have leaves on the left, and sometimes we only have them on the right, and sometimes we have both, and sometimes they have none, and sometimes they're broken. Sometimes you have things called degenerate binary trees. It's a bazillion different ways, and if you think about the slides, there's different ways to traverse this binary tree. There's different ways to store data in it, but that's basically what's going on, what I have here. Let me do that, pointer out. So, and data. So basically, if I were to draw that, it would just be that. Okay? That's a binary tree. And you might be thinking to yourself, why in the name of heaven am I going to drive myself insane and store my data in some crazy middle level construct like that that's probably just going to get in the way and be confusing, and I'll have to remember it, and boom, boom, boom. Think about things this way. Up top here, I've got a node, right? And it goes down to a left leaf and it goes down to a right leaf, and technically that's the smallest thing that can be considered a binary tree, right? This node right here, what does it have coming off of it? Another binary tree. What is this having come off of it? Another binary tree. Binary tree to a binary tree to a binary tree. You kind of get what I'm going for here? Binary trees lend themselves to being attacked with recursion. Okay? What do I have? Do I have a right leaf? Yes. Do I have a right leaf? Yes. Then do the same thing again. Right leaf, yes, do the same thing again. Right leaf, yes, do the same thing again. Right leaf, no. Tail condition. Okay? No, I don't have a right leaf anymore. Well, then let's go back up the stack and perform some operation. Do I have a left? Yes, do it. Go back to the thing. Go up one. Do I have a left? No, then go back up. Go back up, up. It lends itself to recursive operations, and as you get further along in computer science and start learning about the things that we do store in binary trees, we can do sorting with binary trees. You're familiar with binary search, but if you store your items in a tree in a certain way, you can easily search it using recursive methods and things along those lines. Binary trees lend themselves to being attacked recursively. So a little bit beyond the scope of what we're trying to do here, just trying to get you some exposure, just trying to get you to have the very basic information about what binary trees are and the different things that we do with them. So we're not going to go into it psycho, but if you want to, go right ahead. Google it. Google Python space binary trees to your heart's content, and you will learn about red-black trees and AVL, and you will learn about things that will make your brain hurt. But the pain goes away, and afterwards you got some pretty neat information in there, so you'll probably be in good shape. All right. So that is it for the data structures that we're going to look at in Unit 6. Stacks, Pez dispensers, queues, line at the grocery store. Linked list, a way to have a list where our memory items aren't all in a row. 1, go here. 2, go here. 3, go here. 4, go here. So we can dynamically allocate our memory and we don't have to have it all in a row. And a binary tree is just a different node structure that has 3 different spots. I'm going to draw one last thing for you because I do want to make mention of it. Like when I have a binary tree node, I have data, and I have a pointer here, and I have a pointer here. Well, I could have the same node structure, okay? Data, pointer here, and pointer here. But I don't have to do a binary tree with it. I could do what's called a doubly linked list. I could have the first pointer in the list be what's called null. And then I could have this point to this, and this will point to this, okay? So that is doubly linked. So let's say I have 3 items. Holy parallelogram, Batman. So that's a D. That's going to be equal to null because it's the end of our list. I think that's going to be that might be a test question somewhere. So this points to this, and this points to this. Now, what's the difference in functionality than our regular singly linked list? Think about it. In the singly linked list, if I was at the 3rd item and I wanted to get back to the 1st, I had no way to do it. I was out in space because I don't know where I came from. Remember, in a singly linked list, payload, where I'm going. That's all I know. I don't know where. There's nothing here telling me where I came from. Okay? I'm out in space. I can tell you where I want to go to get the next item, but that's it. All right? If I have a doubly linked list, I have the option of going backwards. Hey, I'm in this spot. What's the thing that came before me? Bloop, I know, because I can go there. All right? That is the same node structure as a binary tree, because a binary tree, payload in the middle, 2 things, only they go down and they point to their branches. Okay? But that's, that's the way we think of them in our minds. Technically, as far as a computer is concerned, the same structure. Node has the same structure. All right? I digress. I don't want to get crazy and confuse your students. Okay? So that's it. Stacks, queues, linked lists, binary trees. Now you get a little bit of flavor, get a little bit of survey for what we're talking about when people say data structures. Now, you can go online and say data structure space Python and look in the collections library and learn all about sets and learn all about Q and DQ and stacks and all of the different data structures that there are for you to use in the future with your programs. Hash tables, associative arrays, dictionaries, all these things, they're just data structures. They're just ways that we store our data that we know certain algorithms work on. All right? All right, good. All right, announcements. And I know you can't see me and I can't see you because I'm sitting in my dining room, but this is the last time we're going to get to talk to each other because if I only do the one video for Unit 6, and in 10 days we're done. In 10 days I am putting in the grades for your final, well, no. In 13 days I'm putting in the grades for your final project, but in 10 days you're getting it to me. So the course really only has 10 days left, all right? Hans has finished grading the extra credit assignment 1. So tomorrow, Saturday, I will be sending out Unit 4 grades. My apologies for them being late. Also, over this weekend, Hans will be grading Unit 5 deck of cards assignment. So hopefully I'll be sending out those grades early next week. Just so you can get up to date, know where you stand. I think everybody is doing great. I don't think anybody is in danger of failing. There's 0 worries. I want everybody to concentrate on learning Python and doing well on that final project, okay? Design document, I'm assuming everybody gave it to me. I haven't collected them yet. I might do that tomorrow. Then I'm going to look at those, but those are going to be graded when the final project is graded, so you don't have to wait for feedback on that. Just go, 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 go on your final project, okay? Unit 6 housekeeping, I'm going to probably later tonight, if not later tonight, tomorrow, I am going to release the homework assignments, so you will have them to work on. Your syllabus says that Unit 6 ends December 15th. That is not the case. I'm going to give you all of next weekend to deal with it. So we will close Unit 6 on December 19th at midnight. Okay? That's Monday. That will give you an extra 4 days, so you should have no problem with that. I will do the Unit 6 quiz. Ready for this? I'll probably open it up at 8 p.m. on Saturday and give you 2 calendar days to do it. I'll open it up on Saturday. I'll give you all day Sunday, and I'll give you all day Monday. All right? Because I want you to have the convenience of doing it whenever you want, and I'm not looking to bust your hump with Unit 6. I want you concentrating on final projects, okay? So I'll give you 2 days to do that. It's not hard. The Unit 6 quiz is not that hard, okay? Go look at the last 10 minutes of this video, and your Unit 6 quiz is done. What else do I need to remind you of? Go do SIRS if you haven't done SIRS yet, but that sounds self-serving and it's creepy to say it. So, concentrate on the final project. Work with each other. Make sure that rubric is met. The rubric is the important thing, okay? Make sure everything that's in there you touch upon in your code. Second thing, understand what the word demonstration means. Your YouTube video, PowerPoint presentation, Prezi, should be a demonstration. I don't want you just to report out results and this is what happened and I want to see what's going on. Okay, and you could do it in slides. I want to see your code working. I want you to generate some results. I want you to talk about those results. It doesn't have to be psycho long. 10 slides, 15 slides, that's fine. Voiceover if you want. You don't have to if you don't want. But I want to see the code working. Demonstration. If Hans and I try to run the code and it blows up, we're not going to have a whole lot of stuff to grade you on. So you had better be demonstrating it properly and make it look good and make it fun. But we want to see it being used. We will definitely take the word demonstration seriously. Okay? Oh, what else is there to do? Make sure you do that forum post. The forum post is the deadline on that, and I'll do all the deadlines. You know me with the announcements, so you'll be fine. I will obviously hold that off until December 19th as well. So the quiz will be open for 2 days at the end of the unit. You'll have until the 19th to do the Unit 6 assignment and or the extra credit. And you do the forum post by the 19th and you'll be fine. Final project, I'm going to extend 2 days as much as I possibly can. I have an email out to the MBS office so I can confirm I have to have grades done by 5 p.m. on the 23rd. If that is the case, I will accept them on midnight on the 21st. And that way Hans and I will have the 22nd and the beginning of the day of the 23rd to grade all of them and then get your grades posted so that you can graduate if you're graduating in January, or at least know what your grade is and be able to enjoy the holidays. So I always try to get people as much time as possible to have with their final project. You cannot put the final project in late, and don't miss the final project. My God, it's so many points, it's ridiculous. All right. Then I think we're good. This was a good class. You guys were a good bunch. I wish we had seen each other more. Thank you. You have my heartfelt thanks for putting up with all my insanity with my leg and me having to do the 2 classes online and other things along those ways. I wish we could have met in person more because we would have been able to talk about different things and maybe you could have gotten some, different answers or worked with your classmates more. I do like the component of a course where people get to sit there and see each other. I almost think the hybrid format once a month is maybe too sparse, that it should be once every 3 weeks. Or maybe once every other unit or something like that. I don't know. I think it's too few times during this semester, and it was definitely too few times during this semester with us because, I had all the trouble with my leg and I had to be in the hospital and doing all those other things. But thank you. Thank you for going along with me and getting all this stuff done. Lastly, you guys did great. Think about it. You're Python programmers now. Isn't that cool? You're a computer programmer. Don't let anybody tell you different. You now are easy in the upper 5% of people in the world who do, things with computers or things with information technology. You know a computer language. You are in that high level area where you can actually code. You can actually write programs for computers now. And you may not think it's that big a deal. Everybody knows how to program. Everybody knows that. You know what? Bullshit. It is a good deal. It is a big deal. It's a very big deal. So pat yourself on the back and give yourself a little bit of credit. It's a nice little accomplishment. And especially with data science, knowing Python, I mean, that's the language of data science. That's what you want to know. Python and a little bit of R, and then you're off to the races. All right? All right. Then I am getting out of here. Every once in a while, in the next 6 months, a year or so, check back in with the MBS, because I'm working on some different projects right now, and I'm actually teaching a course, scientific modeling, over at the Graduate School of Education next semester. But in the summertime, I may sit down and try and craft a Python 2, where we actually sit down and we use pandas and sklearn to do machine learning. And we take everything we learned in Python and actually do some data science-y stuff with it. Now that you know what you know, think about it. And think about where I was in September. You got to learn to walk before you can run. So you had to learn Python. And there was no other way to teach you Python except to do what we did. I mean, I can tell you that now because you're all Python programmers. But there was no way after 2 or 3 weeks we could just jump right in and say, this is how we use pandas and blah, blah, blah. You can't. It always fails. There's always half the class is like, what? What are you talking about? Because not everybody is a programmer. I have to assume people are coming in without a lot of knowledge. Now, I know some of you were programmers already, so, things were pretty slow and easy for you in the beginning. But you got to remember, some of your classmates, they didn't know a thing about programming beforehand. So I got to go along at a pace that's, master's degree at Rutgers pace. It's challenging and there's a lot of work, but as far as the concepts are concerned, I got to teach everybody how to program first before we can do data sciencey stuff. But now you have that. So now maybe, hey, let me learn how to do frequency stats with Python. Let me learn a little more about matplotlib and the graphs we can do. Hey, let's do linear regression with this stuff. Let's do some computational modeling. Let's try and do some Monte Carlo simulations. Let's try to do, machine learning. Let's do nearest neighbor. Let's do, naive Bayes, blah, blah, blah. There's a bazillion things we can do now because we're Python programmers. Anything I just mentioned, just Google it. Boom. Python code's going to pop up. You can run it. You can use it. You can start attacking your own data with it. So you're there now. You got no worries. I'm getting out of here. Thank you so much for being great students. Congratulations on being Python programmers. It was a challenging semester with me, with all this, nonsense with my leg, but I think I'm on the other end of it, and I'm super fortunate that I had a bunch of students like you guys when this stuff happened to me, all right? Then I'm getting out of here. You be good. Work hard on that final project. I'll be inundating you with announcements between now and the 23rd, as you know that I will do, all right? So you be good. I'm getting out of here. Thank you. Bye.